Okay, good morning. We're going to talk today about estimating radicals. And we're going to need to be able to do a couple things here. We're going to have to estimate radicals to the closest integer. And we're going to have to be able to estimate radicals to the closest tenths and hundredths place, and maybe even thousandths place. We're going to go over all of that. So estimating radicals, TOC, table of contents for today. I believe it's on page 21. I don't have my regular notebook at home, but I believe we're on page 21. Okay, so things we need to know. If you remember back when we started real numbers, we talked about the real number family and how it broke down into other families, right? It broke between rational and irrational numbers. Rational being able to be written as a fraction, irrational not being able to be written as a fraction, but they were both part of the real number system, okay? And in general, every family of numbers can be represented on a number line. And on a number line where equal increments separate numbers. I get a little better here. Okay, and what that just means is, for example, if we were going to look at a whole number line, so I make a number line of whole numbers, and we can say, well, this is 0, this is 1, this is 2, this is 3, this is 4, etc. And each one of these are separated by an exact equal amount of space, okay? If I wrote a radical number line, I could have radical 1, radical 2, radical 3, radical 4, radical 5. Again, each separated by an equal amount of space, okay? So what we're trying to do when we're estimating roots, we're actually trying to find out what number, right, what real number or rational number equates to that irrational radical, right? Because that produces an irrational number. So what we have to do is we have to take these two number lines and lie them on top of each other, okay? And it's not going to line up exactly. Radical 1 isn't going to line up, well, it is going to line up with 1, but radical 2 isn't going to line up with 2. Radical 3 isn't going to line up with 3. Because in order to be equal to radical 2, it has to, or be equal to the whole number of 2, that has to be radical 4, okay? So when I think about lining up these numbers, and I'm going to put a little bit more increment between here. So if we say this is 0, we're going to say this is 1, 2, 3, 4, 5. You notice the same equal amount distance between the numbers, 6, 7, etc. And I wanted to match them up with their radical counterpart. Well, radical 1 is what's equal to 1. Radical 4 equals 2. Radical 9 equals 3. Radical 16, radical 25, radical 36, radical 49, etc. Okay, but all because we're lining them up, that means in between here, if I looked in between the numbers 4 and 5, all the other radicals from radical 16 to radical 25 exist. So how do I take this space and divide it equally among all of the different radicals that have to fit in between there? That's what we mean by overlaying the number lines. And we're going to talk about how you do that. So let's look at our estimating to the closest integer. And just so you know, I forgot, we're going to need 21 and 22 here for today. We're going to have our rule for step. Step number 1. Use perfect number chart that you're given, or your calculator, or maybe just in your brain if you know the perfect numbers. Remember, these are your perfect numbers. 4, 9, 16, 25, 36, 49. Those are perfect numbers because when we take the radical of them or the root of them, they give us an integer answer or a whole number. Use perfect chart to determine which two perfect numbers the radicand value lies between and their root values. Okay, so that is step number 1. Step number 2, calculate the range of the large perfect number, which we're going to call LP, and then number, large perfect number, and the small perfect number. So LP number minus SP number, and divide by 2. So we're going to take this and then divide it by 2. That's step 2. And step 3. Add the value that we just figured out in step 2 to the small perfect number. Okay. If our radicand value is greater the root of the large perfect number is the closest integer. If Radicand value is less than what we came up with, the root of the small perfect number is the closest integer. And then lastly, of course, we should have our answer. Okay, let's go ahead and do an example here. So radical 57. Well, radical 57, if you looked at your root chart, falls between the smaller perfect number, 49, and we know the square root of 49 equals 7. And the large perfect number is 64, and the square root of 64 is 8. So we know that if we actually perform the calculation, the radical of 57, that our answer is going to fall in between the two integers 7 and 8. Our goal now is to determine, is the radical 57 closest to 7 or is it closest to 8? We're going to do this by hand, and we're going to show you how to do it on a calculator. But we need to know how to do it on hand because definitely in the standardized test, you will not be given a calculator to use to do this.